Hello, everyone. Welcome to the first planetary science lecture where we're going to talk about planetary properties. I just wanted to go over the overview of this exciting topic in planetary science. We're going to talk about the properties of planets here to begin with. Then we're going to look at all the atmospheres of the planets, take a tour through each atmosphere. We'll look at how magnetic fields are generated and how that relates to planetary interiors. We'll look at the surface features of planets. Because Venus and Mars are so close to us, we're going to talk about each of those individually. We'll look at the moons in the solar system, lots of great, interesting worlds out there that are circling our planets. We'll talk asteroids, comets, and meteoroids. We'll look at the very formation of our solar system and then look at some solar systems outside of our own sun, other planetary systems, in our discussion on exoplanets. So let us begin with our discussion of planetary properties. So first of all, what is a planet? A planet is a body that orbits the sun or central star. It has sufficient mass for self-gravity to create a spherical shape, and it has cleared its orbit. The Earth, for example, is orbiting the sun. There is no other large objects in the orbit around the sun in Earth's orbit. The Earth has cleared out most all of the asteroids and meteoroids and things hanging out in space around it. Earth is much bigger than its own moon, so Earth is a planet. Pluto is not a planet. Pluto is orbiting the sun, but its orbit is slightly tilted from the rest of the planets, first of all. That would be okay. And Pluto is spherical, large enough to be spherical, which is great, but Pluto hasn't cleaned out its orbit. Pluto has a moon, Charon, that's almost as big as Pluto, and there are several other odd kinds of objects floating around in the orbit around the sun around Pluto, and these are called Kuiper Belt objects. The area around the sun, comets and planetoids out there that are orbiting with Pluto cause Pluto not to be called a planet. Um, the distances in our solar system are measured with astronomical units. One astronomical unit is about 93 million miles or 150 million kilometers. And that is because we needed a measuring system in our own solar system that made more sense than kilometers, because talking about uh, hundreds of millions of kilometers, it's easier to use a more standard unit of measure. And so, standard unit of measure in the solar system and our own planetary system is the astronomical unit. When we view things in our sky, they appear to be a certain size, and actually, those are angles. If we think about it, our eye is a single point in space here on near the surface of the Earth. And when we look out at objects in the sky, the object is basically an angular size, kind of one side of the object to the other. You extend those two lines on both sides of the object back to your eye, and it actually strikes an angle or an arc. Um, your fingers and hands can be used to measure angles in the sky. Your finger extended at arm's length about 2 degrees wide. Your fist extended at arm's length about 10 degrees wide. The moon, as an example, from one side of the moon to the other, it's about a half a degree of arc wide. And so we measure things from angles in our sky. We talked a little bit about this when we talked about our sky. A reminder to you that when using angular diameter, or the size of something in our sky, these objects are really small, obviously. To give you a comparison, one arc minute across is like standing on one side of a football field and having a friend stand on the other side of the football field and hold up a quarter. If you hold the quarter up and they say, "Okay, can you see the quarter?" That is about one arc minute across. And if your friend turns that quarter, takes it and puts it away and takes out their ballpoint pen and clicks it and says, "Okay, now look, can you see the tip of my ballpoint pen from across the football field?" That is one arc second across. So we're talking about very small distances. Obviously, telescopes are helpful in using and measuring angular diameter. Here are the planets as they appear from Earth from the same magnification, and you can see the varying degrees of angular diameter. You can see that Venus is obviously actually the largest object in our sky when it's closest to us. Its angular diameter is even bigger than Jupiter's angular diameter. Um, and you can see the rest of the planets from the same magnification, how big they appear through a telescope at the same magnification. These are the angular diameters. And as it stands to reason, the angular diameter is mathematically related to the actual diameter of the planet. Obviously, Jupiter is much larger than Venus. In fact, Venus could fit in the red spot of Jupiter, but nonetheless, Venus appears bigger in the sky. This is because the angular diameter of Venus is bigger because it's closer. So, angular diameter, you can actually calculate the angular diameter, um, or sorry, calculate the actual diameter of a planet using angular diameter and distance. They're mathematically related. And I have a little diagram showing the mathematical relationship there. You're actually going to use that in our little planetary science mini lab on angular diameter. The actual diameter of an object is equal to 2 times pi times the distance of the object away from us times the angular diameter divided by 360. You can actually also determine the planet's mass by looking at how the moons orbit the planet. Um, Two bodies orbit around a center of mass, and if the moon is orbiting closer or further to that center of mass, it can give you an indication of how actually big and massive a planet is. So just throwing that out there that you can actually measure a good accuracy, a good amount of accuracy, the mass of a planet by looking at how its moons orbit it. In general, we talk about planetary properties. It's good to note that there are two types of planets, terrestrial and Jovian. The word terra means Earth, so the terrestrial planets are the Earth-like planets. They're the four planets closest to the sun. And of course, they're rocky, so they are relatively small and high in density. And because they're small, they have thin atmospheres. Typically, small gravity things have thin atmospheres. We'll talk more about that when we look at planetary atmosphere. The Jovian planets, in contrast, are the four planets farthest from the sun, and they look like Jupiter. They're relatively large. They're mostly gas and liquid and some ice. They're low in density as a result, anywhere from zero point 0.7 to 1.7 in density. And they have thick atmospheres, lots of gases like hydrogen and helium, some methane, and others. And it's of note that the Jovian planets are much larger than the terrestrial planets. They're often referred to as the gas giants for Jupiter and Saturn, and Uranus and Neptune are referred to as the ice giants. And why is it that the planets outside of the orbit of the terrestrial planets are so large? Why are those planets big and the terrestrial planets small? It's because of what we call the rock metal line and the frost line. Planets inside the rock metal line are too close to their star, so they can't really form up. It's just mostly gases and liquids in there, so very difficult for planets to form up. But once you cross the rock metal line, rock and metal start to be solidified into a solid form, and so they easily come together to form planets. Thus, the terrestrial planets are mostly rock and metal. When you get outside of the rock metal area and get into these cross these so-called frost line, this is where ices form from the common gases that we see. The gases of things like hydrogen, helium, ammonia, methane, they all turn into liquids and solids past this line, and as a result, they're more likely to come together in the formation of the planet. So planets outside the frost line typically are larger, they have more gas, um, and they are composed of more ice as well. The Jovian planets do have silicate rocky cores, we think, but they do have a lot of that ice. So that is a look at some of the basic planetary properties. We're going to talk about planetary atmospheres next time. Thanks for listening.